It's okay.
Okay.
Well, so first we had a little bit of game theory. Now we're going to have some waves. So for me, it's really a great pleasure to introduce Professor George Papanicolaou. That was very nice to have him come here to IMPA for the first time in '95, exactly 1 year after I joined IMPA. It's really a great pleasure to see George coming here more frequently, interacting with IMPA, with Jacques, and hopefully this will last for the next 50 years, right? So it's really a great pleasure, and today's George's talk will be on time reversal imaging and communications in random media.
Okay, thanks, Andre. And congratulations to IMPA for its 50th anniversary. It's a thriving organization. I need not tell you this. I discovered IMPA rather late, as he said, in 1995, but I'm hooked. I've been coming every other year. It's a great place to come to work, and it's a very exciting environment, a unique mixture of pure and applied math. So what I'm going to talk about today is time reversal and imaging and communications around the media. I have a list of collaborators, a long and interesting list of people. We formed a little consortium. It's an informal thing. I read their names: Liliana Borchea, Crisula Tsonga, Jim Berryman, Peter Blomgren, Lenia Rizik, Knut Solna, Honkai Zhao, Guillaume Bao, Jean-Pierre Fouque. And Andre is involved also. We have some honorary foreign members, including André and Jocelyn Garnier, also from France. So this is an exciting research group that we start with, research area and a research group that we started about in the fall of '98, almost 4 years now. And so it started from a lecture that I heard at Stanford in the mechanical engineering department from Dave Dowling, who had done some experiments in time reversal, and it looked like an extremely interesting subject. We got slowly into it, and then we realized it's an extremely complex and interesting research. Mathematically, it's a very complex subject. So this is a cartoon from the November 1999. Is there a pointer?
Yes, there should be. I can do
Well, okay, that's okay. I don't really need it. So, no, that's okay. So this is a cartoon from the November 1999 article, Scientific American article by Matthias Fink, Matthias Fink is a physicist who started out about 12 years ago. He's a physicist who started out in solid state physics, and maybe about 30 years ago, and then in the early 90s he realized that time reversal, which is the cartoon of here, is very interesting, and he has now a lab in Paris that is doing the best experiments in the subject. Very interesting, very exciting work. So here's what time reversal is all about. Time reversal is based on a device, that yellow mirror that you see there. It's an active device, a time reversal mirror. So you shout at this mirror on the wall, and it receives the sound signal. It receives it, stores it, and then after the signal has stopped arriving, the end of the signal, it time reverses it. The things that arrived last get sent out first, and sends it back. Oh, there you go. Sends it back from now here it's being received, here it's being time reversed, and let's see where it's going now. Okay. I can get, okay, here, my cursor, okay. So I have the, it's being time reversed, and now it's being sent back, and you can see that it focuses right into the mouth of the speaker. In other words, it has the ability to retrace its step. The waves retrace their paths through the medium and converge back onto the source, approximately, of course. So it's actually an interesting experience. I was told when you stand in front of this mirror, you yell, and the signal comes right back to your mouth, and it vibrates your head. Of course, it comes back time reversed, ole. It doesn't come hello as it came out. So the question is, what's the mathematics behind this? And what's more interesting is what happens when you have inhomogeneities in the medium, when the medium is inhomogeneous. So here's a schematic. It doesn't look very clear, but I think you can figure out what it is. Here's a schematic. You have a source at the point y, and it's emitting a spherical wave pulse. It's time domain phenomenon. And the pulse propagates out until it strikes. This is the array of transducers, receivers, transmitters. It's an array, it's a dense array of transducers, meaning that the transducers are placed rather closely to each other, like half a wavelength. The central wavelength here is of the order, for example, in these ultrasound experiments, or the ones that are done by Fink, the wavelength is about 1 millimeter or less. It's of the order of 1 megahertz, the frequency, ultrasound. And so this is really an array of about 120 transducers. It's about that big. It's about 10, 15 centimeters big. And so the signal is received at the array. You can see that the little trace of the signal, as it is being received, then it's stored, it's time reversed, and it's sent back into the medium, and then of course it tries to focus at the point where it came from. That's the basics of the time reversal problem, the geometry. There are 3 parameters here, 3 length scales that are crucial in any kind of understanding of what's going on. One is the range, capital L, which is the distance between the array and the object. How far are you? The other one is the carrier wavelength lambda, which let's say is usually much shorter, is of the order. I mean, here it might be that you go 1 meter or half a meter, and then of course the wavelength is 1 millimeter. The array size, which is the number of array elements divided by, or the number of gaps, or the number of array elements divided by multiplied by lambda over 2, the gap between them. And typically we are operating in this regime where the wavelength is very small compared to the array size, and the array size is very small compared to the range. That's the so-called remote sensing regime, high frequency remote sensing regime, where interesting phenomena can occur. If, to put in some numbers, I think I have them a little bit later, a similar situation occurs with microwaves, in the regime of wireless communications, where the wavelength would be about 20 to 30 centimeters, propagation distance would be about 1 or 2 kilometers, and the arrays would be fairly sparse, would be just a few, would not be too many of them, but would be of the order of a couple of meters. So here's a little bit in more detail what how time reversal is quantified, its performance. And this is the calculations behind this are classic calculations that were done more than 100 years ago in connection with optics, because as you will see here momentarily, the time reversal mirror is really behaves as a broadband, as a lens, broadband meaning in the time domain. So you have here the source. The source emits the spherical wave. The spherical wave arrives at the array size A, this is L. And then when you time reverse and send back the signal, it does not focus precisely on the spot. It focuses with a resolution that is proportional to the wavelength multiplied by the range and divided by the array size, lambda L over A. This formula is a classic formula, which was first derived by Rayleigh more than 100 years ago, 130 years ago. And it's so-called the Rayleigh resolution limit, or the diffraction limit of, it's the same one that is used in optical instruments to find the resolution, which is a function of the aperture of the array, how far you are, and the wavelength. Now, the horizontal resolution at the single frequency, narrow band, is much worse. It's like this, but, okay. And so here I repeat some of the numbers for wireless communications. These are the numbers. So yeah, an interesting thing is if you put in the numbers, so this is a phenomenon, time reversal, and you might say, how come all this brouhaha in the last 10 years and people, this is not such a very, it's something that people should have thought of a long time ago. Yes, of course, but here's the reason why it wasn't of interest until this phenomenon, at least the random media came in. And that's because if you look at how time reversal in the wireless situation, how it would refocus, if you put in the numbers lambda equals 20, A equals 2, L equals 5 into this formula correctly, you end up with a cross-range resolution of 500 meters, which means that time reversal in the wireless situation, there isn't any refocusing to speak of at all. 500 meters is hardly anything to talk about. So the Rayleigh resolution limit, which is hardwired into people's heads when they think about these things, discourages you from thinking of a time reversal mirror as a lens, as an instrument for probing, for doing things with it. Until people I think this really genuinely happened about 10 years ago, is what happens when the medium is randomly inhomogeneous. Something rather spectacular happens, which is what I want to describe to you. And before I explain to you the phenomenon, let me first give you the result of a numerical simulation, which is a completely, it's an experiment that is perfectly well controlled. We know exactly what we're doing, and we can measure the outcome very effectively. So here's the numerical domain. We're solving the wave equation, the acoustic wave equations. Let's think of the time-dependent wave equation. And we solve it with a finite element code in a time domain with very high resolution, 40 points per wavelength, roughly speaking. It's a very highly resolved problem. And so here, I don't think you can read the numbers here. This is going 40, everything is measured in wavelength. The range is 48 wavelengths. This is supposed to simulate things, to be a situation like in Fink's experiments in ultrasound. This is the array. The array is about between 10 wavelengths. It's of the order of 10 to 20 array elements. And the width of the region is 24 wavelengths. Now the pink border around it is a no reflection layer, a perfectly matched layer, PML as it's called, that does not reflect the waves. Numerically, the waves, when they hit this pink region, they get absorbed there. They don't come back, to simulate an infinite medium. And now the speed of propagation, the sound speed, is not a constant. The sound speed is, let's say, 1.5 kilometers per second, as it would be in a liquid. And here, you see the fluctuations in the sound speed plotted in a color plot. Here is the fluctuation, the variations in the sound, about the average, the fluctuations. The fluctuations can be of the order of a few percent in this experiment. And you can see that from the density, from how close the blue spots and the red spots are to each other, you can get a feeling for how the peaks and valleys are correlated to each other. The correlation length, which is the correlation length is a well-defined quantity for a random field, two-dimensional, a random function of two variables, is of the order of the wavelength of 1 millimeter. So you can this is in millimeters here, the scale. So you can see that this is varying on the scale of millimeters. So we send a wave, the source is over here. At this point, we send a wave to the array, we receive it, we store it, we time reverse it, and we send it back in, and we want to know how does it focus back on the source in the presence of the inhomogeneities. And so you see here, what this is in the top figure, you have no inhomogeneity. It's a uniform medium. The refocusing is at the time the peak of the wave arrives at the source. You look at the transverse resolution, the cross-range resolution is of the order of a few millimeters here. But when you go to the random medium with about 5% standard deviation fluctuations, you see it's nearly, the spot size is down to half its size. It's maybe even 50% of what it is here. How did this happen? How did it happen that in a random medium the refocused pulse beats the diffraction limit by a substantial amount. Even in a simple experiment, there are situations where it beats the diffraction limit by a factor of 10, and maybe even more. So that's the interesting phenomenon to analyze and to see what's behind it and to exploit it. So here's I'll try to explain the cause of this phenomenon is multipathing, is multiple scattering. It's precisely the sort of thing that you might intuitively, that's what happened to me, intuitively you might think would obscure the whole process. Every time somebody would tell you that a dirty lens would perform better than a clean lens, it's not exactly the most intuitive thing. Or you put a lens in a dirty medium and it will perform better than a lens in a clean medium, the focusing business. Well, that's what's happening, because what multipathing does is you have this point source here, and you see typically a path, a ray of light or a ray of the wave that will depart from here will not arrive as a straight path, or it's very unlikely. Most of them will not survive. If there are between here and here, they are of the order of, let's say, 50 correlation lengths in the fluctuations of the medium. The chances that you will scatter out of the line of sight between the transducer and the array are very, very good. So a relatively small number of direct rays will be received. But on the other hand, some rays that would have gone all the way in a different direction now get bent into the scope of into the region where they can be captured by the time reversal mirror. So here I have the expression, the mathematical expression for the field that is refocused. So yeah, and now when you go into so you receive the signal, and then when you time reverse it and you send it back, you can see that the waves retrace exactly their path. The medium is time homogeneous. The wave equation is completely time reversible. It's a mathematical fact, and this is reflected by the expression I've written here, that the waves that are re-emitted, time reversed and re-emitted, will just follow exactly the same paths from which they came. And therefore, when they go and they focus back on this spot, the Rayleigh resolution limit will not be lambda L over A, but lambda L over A effective, a new aperture, effective aperture, which is something that must be calculated, which says that, in fact, this array appears to be a lot larger than it actually is physically. The physical size of the array is not a relevant object, but somehow a wider angle of rays is approaching back here and is contributing to the refocusing, as if the array had captured rays that were going in very wide angles. So it appears to be a broader aperture. So let's see, mathematically what we have is first of all, this is the point Green's function, the Green's function for the wave equation from the point, yes, I think here the observation point y0 and the source point are interchanged in this formula. So this should have been y and this should have been y0. So you start from y, and this is the Green's function that takes you from y to xj, multiplied by the pulse with the Fourier transform of the signal, the time signal, f hat of omega. So this is the complex amplitude in a Fourier space. This is what is received at the jth point in the array, at xj here. This is what is received. Now the complex conjugate corresponds to time reversal. And then this is the amplitude that now you're going to send back from xj to the observation point y0. y0 is an observation point in the vicinity of the source y. So the field that you see at the observation point y0 due to a source at y as a function of time is this gamma, is the field that you observe. The y is unknown to you. You don't really know where the source is. You have the observation point y and the time t. And this is a random function. It's random because the Green's function is going through this randomly inhomogeneous medium. So you would like to know how this function peaks in the vicinity of y0 equals y at the time that corresponds to the arrival time to go out and return. This expression can be analyzed completely mathematically. It's not such a very hard problem. You go into a regime where some asymptotic methods can be used, and you find several remarkable things, which is there on the next slide. You can calculate the point spread function, the degree of focusing of this expression. But the most interesting thing about this is, yes, you can get the point spread, the focusing. The most interesting thing is that this function is self-averaging. It has the property, all of a sudden we run into a situation where ergodic properties of stochastic differential equations come in, and here's a phenomenon whereby this expression, gamma hat, in the frequency domain, one frequency at a time, the Green's function conjugated multiplied by the Green's function multiplied by the f hat, this object is highly fluctuating as a random function for different realizations of the medium. But but if you have a broadband signal, you have some diversity over frequencies. You have a broad band of frequencies that you're summing over to reconstruct the signal in the time domain. Then this self-averages because over different frequencies that are not too close to each other, there is observed a kind of a decorrelation. Therefore, averaging over frequencies is a little bit like averaging over realizations. And so you end up with this statement that this gamma is self-averaging, very close. Without you doing anything, it's very close to its mean. And therefore, it's stable. You observe it. So if you go back to that numerical experiment that I showed you before, here, if you go to the random medium case and you keep changing the realizations of the random medium are created with random Fourier series. So you keep changing the random Fourier series, nothing budges here. This little spot, the medium changes dramatically, different realizations, same statistical properties overall, but different realizations. This doesn't change at all. It's completely stable, which is what this self-averaging is doing for you. So then, of course, you have the effective aperture. That the effective aperture is much wider than the physical aperture. And here there's an analytical formula that can be derived. It's not very hard to do. And you see that the effective aperture is the square root of the sum of the square of the real aperture, the physical aperture, a squared here, plus a constant which has the dimensions of 1 over length, that's characteristic of the random medium, and then L cubed, where L is the range. So what this is saying, this is a highly idealized situation. It says in an infinitely homogeneous random medium, the further away you place the mirror from the source, the bigger the effective aperture appears to be, like L range to the 3/2 power. That could be, you could get a factor of 10 out of this very easily. Now there's a downside here, which is that yes, this is what happens. The spot size decreases, but also the intensity. You lose some energy because of the scattering out of the array, and so that's not shown here, and that has some implications. They're not absolutely dramatic in some situations because you can amplify the signal before you time reverse it, but eventually they are a limiting factor. So those are the basics of time reversal. Yes.
Array instead of a random one?
No, because in a periodic array you will get very sharp resonances, and so what will happen is that you will get side lobes. You will get, for example, in the vicinity of the point where it should focus, there would be ghost focusing points at certain distances right off of it. Okay. What you need is in fact, what you would like to do is you would like. If you were in a waveguide, you would see this, and what you would like to have is you would like to have some diversity, either to have a lot of transverse modes in a waveguide or a lot of frequencies, diversity in broadband in the frequencies, that somehow the Fourier series that generate a solution has enough diversity that no sharp peaks appear, okay, off of where they should, the principal one. It's an ergodic theory that I'm explaining to you. So applications and the history of time reversal. This is my slide, my historical slide, where things are coming from. So I think I have this history accurately. I always am a little bit nervous that I've forgotten something or I overlooked some field, because people are aware of these things in different contexts with different names and different jargon and what have you. Okay, so it looks like the first time or phase conjugation. If you deal with monochromatic signals, with signals that are not in the time domain, but they are at a single frequency, this business of time reversing and send it back is equivalent to phase conjugation. You have a signal, which is time harmonic. It is received by some array, and then it's phase conjugated and sent back. Instead of normally when you have a signal, it's reflected, it goes in this way. When it gets phase conjugated, the signal comes here this way, reflects and comes right back at you. That's phase conjugation. This phenomenon of phase conjugation in optics was done in the early 70s. Apparently in the Soviet Union at the time, some experiments that were reported in Physics Today in the mid-1970s. And that led to a number of interesting applications, adaptive optics, applications to laser fusion for focusing energy with phase conjugation onto pellets of nuclear material so that you would not have kind of asymmetric focusing of energy. That was the principal thing that they were interested in. There was a lot of things were kind of couched in Cold War stuff, and there was a lot of stuff was not out in the open. So. But the interesting thing about this, there's a very interesting article about optical phase conjugation that appeared. It's a very, if you remember to look it up, is an article in Physics Today, 1981, by I forget his name right now, but he was the former, at the time, he was the director of a group of researchers at Hughes Research Lab in California, who was doing phase conjugation at the time. And it's a very interesting article because it's a kind of a futuristic article. They explain what the real problems are, what their research thrust is like, how they, a lot has to do with the hardware. How do you generate optical devices that do implement the phase conjugation? It's a nonlinear phenomenon in the optical regime. Nonlinear optics inside the lens that does it. So, what I found very interesting reading this article is what he was expecting in 1981. He was writing, and he says, we're going to do this, we're going to do that, we're going to do this. You read it 20 years later, and very few of the things that he wanted to do have actually been done. And I called him up, I tracked him down. He works now at the Air Force Research Lab in Albuquerque. And I said to him, how come nobody has done this, nobody has done that? And he didn't know. He said he didn't. But I tell you, I know why it wasn't done. It wasn't done because the mathematics wasn't understood. And a lot of the reasons the phenomenon was couched in jargon. It was never really presented in its basic form, what really is involved in there. And I think the subject took off later in an entirely different field, here in underwater acoustics. In the late 80s, it took off because people completely unaware of that it had anything to do with these experimental people. Bill Cooperman, Daryl Jackson, Dave Dowling, they didn't know anything about, or they know roughly about phase conjugation, but these are completely different experiments in the other underwater sound, very broad band, not single frequency like in optics. And they saw all these interesting phenomena, they reinterpreted everything. But the real decisive step was the work of Matthias Fink in the early 90s. He started this lab in Paris where he was doing absolutely precise clinical experiments with ultrasound that were enormously, for me, they were just, it was my Bible. Every time I was confused, I would go back and read the paper of Fink. Which paper of Fink was it that described the experiment? And it was an eye-opener. I knew exactly what I had to do mathematically because he was describing it in such careful detail. And then in the last few years, the wireless communications business discovered multipathing, discovered this phenomena, again, entirely on its own. And now multipathing and time reversal protocols in communication, they're not called that, are all the rage, and there are sessions, very, very large sessions in national meetings and elsewhere on wireless communication. They have the ability, in other words, the idea is that you can use your wireless phone, let's say inside airports, inside buildings, in very cluttered environments, in an urban environment, with no fading and with no necessity to discriminate for multiple signals that are received, not direct signals that are received, and in using base stations, cellular networks that are not so dense as you might think they were needed before, because you take advantage of the multipathing. So the technology is really very rich here. Here I show you this is from the Scientific American article of Matthias Fink, and it shows a cartoon of the experiments that were done by Bill Cooperman and his group at Scripps. But actually this was done off the coast of Italy, near the island of Elba. You can see here there's a NATO base in La Spezia in Italy, and so this experiment that they did was done about, I think, what year was it? It was published in 1996, 97, so it must have been around that time they did the experiment. Here's the boat that drops down a source of signal. It's of the order of, the wavelength is of the order, it's broadband, of the order of 1 meter central wavelength, 1.5 kilohertz frequency. This distance is about 15 kilometers. Very complex environment, very highly diverse, multipathing environment, lots of scattering. This is the time reversal array. That was apparently a very big technological coup in this regime to design design and build a time reversal array like this, which is all the way from the top to the bottom, was about 120 meters here. And then this is the array that receives the signal, time reverses it and sends it back. And this back here is a passive array that monitors how good the refocusing is in the vicinity of the source. So this is a schematic of, I'm sorry, the lettering is not coming out very good. This says the range is 15 kilometers. This is where the source is. You can see this little red spot gives you an idea of how big the pulse is, how wide the pulse is initially. So this is how it is received. This is a cartoon, of course. The idea is here to see that as it is being received, the signal has spread all across. This is a waveguide, by the way. It's not an open medium because the sound cannot escape from this layer of fluid about 120 meters deep. And the signal is spread up and down the channel here. And then you receive it, you time reverse it, you send it back, and it focuses almost on a size, on a spot that is the original one. This is an absolutely remarkable experiment that shows how they focus. There are no side lobes. It's absolutely spectacular how this was done, how this really worked like this. And it's interesting that you might, if you use the Rayleigh formula that I've shown you here, which of course is not quite applicable because it would be, this is for an open infinite medium, you find that the Rayleigh resolution limit for the time reversed spot would be about 100 meters. And of course 100 meters is the width of the channel here is meaningless. So you get really very good super resolution. The theory is a little different, but qualitatively it's the same thing here. Now, I want to explain how the idea of time reversal can be used in imaging. And this is something that we started about a year and a half ago. And we thought that time reversal is kind of interesting, but it's limited. How about imaging? So, well, the imaging problem is a classic problem that's like this. You have this array, and down there, a distance L from the array, large compared to A, in the remote sensing regime, there are certain small objects, targets, that you would like to be able to detect. Just classic radar problem. Radar stands for radio, direction, and ranging. So you would like to find where are these? Can you locate the cross range of these objects and their range? Can you locate these objects? Well, this is an active array. So you send out a signal. This is an array. You send out a signal from the jth transducer. It's a certain pulse in a time domain, relatively well-designed pulse for this experiment. It goes out over this is a multipathing environment. It's a random medium. It's an inhomogeneous medium. So this signal leaves as a spherical wave. It goes and strikes these objects. And these objects, when they are illuminated, they reflect back a spherical wave if their size is small compared to the wavelength. In the Rayleigh regime, they reflect back a spherical wave, and then they each one do so when they are illuminated, and then you receive a signal at the kth transducer, which is, let's say here you get a big blip from the scattering of the closest one, and then another big blip, and so on. So you receive the signal. And you do this for every transducer, and you record for every other transducer, so you end up with a matrix, so-called response matrix, capital N by N. N is the number of transducers. This response matrix is simply the signal in time received at the kth transducer from the jth one. And it's a classic problem. It's an absolutely classic problem in radar or in any other, in sonar, what have you, is from this array, which is usually it's a symmetric array, but it's not even in T. It's not time reversible. From this collection of, from this information, this N by N matrix, to determine the location of the scatters, to determine how many scatters are there out there, what's capital M. Typically M is small compared to N. You have a large array, and find their location. That's the classic imaging problem in its simplest form. There are many other variants when you have many other variants. Anyway, we're in this in the regime of random media and remote sensing. So the wavelength and the correlation length L, little l, are rather comparable to each other. This doesn't have to be like this, but this is an interesting regime. The array is relatively large compared to the wavelength, but it's very small compared to the range, how far out you are. And of course, there is multipathing in the environment. How can you do this? How can you do this detection problem when you're in a cloudy environment? So the idea was to use statistical stability. We know, what did we learn from time reversal? From time reversal, we learned that the physical time reversal, whether you send back from the array the signal, it has very good self-averaging properties in the time domain. Now, what does that have to do with imaging? So why am I interested in time reversal? What does time reversal have to do with this? Here I have this array, I have these unknown locations, I have this information, the PJK, the response matrix. Where on earth would time reversal come into this picture? You might say, look, just simply guess where these targets are, solve the forward problem, guess where these targets are, assume that the medium is homogeneous because you don't have any other information about the medium, okay? So assume that the medium is homogeneous, have a synthetic response matrix here as if you knew where the targets were, compare the response matrix that you just calculated with the data, and then propose some iterative scheme where you would update the location of the scatterers until the some mean square error between the synthetic problem and the real data has diminished. That's a classic boundary least squares method. It's used in seismic programming. People have spent their careers doing things like that and improving them large-scale optimization problems. The point is that when you're dealing with this, you should never do this. This is just absolutely the worst thing to do for a problem like this. You have to deal with a very difficult and ill-posed optimization problem, very large scale. You should never do this. What you should do is, you should say, look, if these were illuminating directly, they were not illuminating the array from a secondary reflection. If these were their own autonomous illuminators, and I received the signal, I would get back to their location by time reversing the signal and sending it back. So why not take this array data, this response matrix, somehow do something to it. It turns out it's the singular value decomposition. do something to it so that it isolates the targets one at a time, and then time reverse this information. But since you don't know the random medium, time reverse in a homogeneous medium. Then, when you do this, the time reverse signal, now on paper, because you're doing it numerically in a homogeneous medium, should go and focus, should have a peak in the vicinity of the real target location. That's a good idea. That's what you should be doing, to do a singular value decomposition. But the question is, how do you do that in broadband, in other words, in the time domain, not frequency by frequency? And how do you do it in such a way that the objective functions, the functions, the functionals of your data that are supposed to have a peak near where the unknown target location is, are statistically stable. Since you don't know the medium and you're time reversing in a homogeneous medium, you don't want the lack of information that you have to interfere, to give you an objective function that is too sensitive to the underlying lack of information that you have. So this is what I have in this slide. I have explained this a little bit. So we really want to account for the statistical stability. Of course, the super resolution. So the super resolution, the extreme tight focusing that you get with real physical time reversal, it's as if you knew the exact microscopic features of the medium, both going and coming back. When you don't know it when you're coming back, this is going to work against you. So the super resolution will introduce a fuzziness into the imaging, but the self-averaging will be maintained if you use the correct functionals here. So there are a number of ways of doing it. One is, I will show one is the matched field method. And so let me go directly to the matched field. So here's a way how you do it. This is a, so imaging, so I'm going to show it instead of getting into the singular value decomposition, which would eat my time. I'm going to show it for a situation in which the target out there is active, is sending out a signal, and you're trying to track where is it. So what you do is, theoretically, what you expect is that this Green's function, you see the unknown, y is the unknown location of the target. So it sends a signal out, which is received at x1, x2, up to xn. This is the vector Green's function. The Green's function, as it is received at the various transducer points, x1 up to xn. This forms a vector, which is a function of the unknown location y let's suppose it's a single target. So this is what you receive. You receive this vector multiplied by the pulse Fourier transform f hat. This is the h is the Hermitian conjugate. Okay. Now you take this, you take the inner product of this with a deterministic g. The subscript 0 means deterministic Green's function. The same thing with a deterministic Green's function here, which is an explicit expression you know, normalized. So this is the inner product of the deterministic Green's function. Okay, you take the inner product, and now you say you take the absolute value of this squared. You get rid of all the loose phases that might be here, and then you inverse Fourier transform. And of course, this function here, being the inverse Fourier transform of a positive function, it has its maximum at t equals 0. So you evaluate this at t equals 0, and you look for the point z for which this expression is max. In other words, you have a test point z. You pretend that you know where the location is. You don't really know where it is, but you look for the z that maximizes this expression. Well, the nice thing about this functional is that it's not so random. This functional, of course, is random, but it's self-averaging. So in a suitable situation, it will be very stable. And so when you go looking for this maximizing point, you will find one that doesn't fluctuate very much. So here's how it behaves. This is the same situation, the numerical experiment that I showed you before. Let me just remind you very quickly where that. Here it is. It's just you have this is again active now. You send it here, and then you try to locate this point now as an imaging problem, not time reversing, but as an imaging problem. So here, is using the, actually here it's a slight variation of the matched field method. It's called music. It's a variant about 15 years ago it was invented. There's a lot of, as you can imagine, it's a field in which small changes in the computational algorithm can make a difference, and it's a kind of very competitive area. People fight to get their method recognized for its improvements here and there. So this is using the music algorithm, and you can see that this is a homogeneous medium. This is the top row, the top line is homogeneous medium results. On the left is time domain. On the right is single frequency. So you can see that in the homogeneous medium, it makes no difference whether you do it in broadband or narrow band. You pick out the target very well because the medium coming and going is homogeneous. There isn't any loss of information. You go and refocus with a Rayleigh resolution limit in both cases. But in the random medium, first of all, you see there's a huge difference between being in the time domain and being in the frequency domain, single frequency, as far as time imaging is concerned. Here, this is very stable. You get this conical region. You don't quite get, the target is somewhere in here. You don't quite get it. You get this conical region. I'll explain to you the origin of that uncertainty region. You get this, but when you go into the frequency domain, you get nothing. You change the realization, these regions dance up and down. The red region is not stable at all. This one is stable, but it tells you that the method, the matched field method that I showed you, is capable of finding the cross range. It tells you from which direction things are coming from, but it cannot tell you what the range is. Okay, to get the range, you have to do something else. You have to look at the data, the arrival times. You have to look at the data, what arrives when. And now it's a different part of the data that you have to look at. And that requires a different theory. And then you try to combine this information, cross-range and range information, in order to do better. And when you combine this range and cross-range information, you can see that you can do extremely well. This is a situation in which you have, let's say, 2%, 2.5%, 2.25% standard deviation, 2.53, 4.67, 3.82. The MF stands for maximum fluctuation. So you can see that even with nearly 5% fluctuation, you get almost a perfect spot, as if it was a homogeneous medium. You can take out the noise. It's a fairly, it's a good result. Now, if you have two targets, then here's what happens when you have no inhomogeneities. Here's with nearly 5% inhomogeneities. Here's nearly with 7%. And now, if you keep cranking up the fluctuation level, sooner or later things are going to break down because you're just not going to be able to do it forever. So sooner the fluctuations are going to look like themselves like little targets. So here you kind of begin to lose it at about 8.5% fluctuations. I have a slide. So this is what I wanted to say about imaging. There's a tremendous amount to be done in imaging. Larger objects, synthetic arrays, large, very synthetic arrays where the array is just being moved across. It's a subject that is just beginning to attract the attention of more mathematical treatment. As I said, the ideas that I described were we just went around and we looked at what people were doing and we selected, as if it were from out there, what were the things that would work well in an environment that had multipathing. We analyzed that. So, but communications is now a subject that is really taking off. And I have one slide. This is my last. I have one more slide with conclusions. And this is, I think, this is what it has the potential of changing our perception of communications altogether. And it says the following. I should have had a graphic here, but maybe I can use the board. I have a few minutes. Thank you. So I have, in a communications problem, I have two things. I have, let's say, here's a situation where I want to, let's say, this is the transmitter, and this is the receiver. Okay, so this guy wants to receive a signal, and we're in a regime, let's say, wireless. It's a couple, say, a few kilometers apart, wavelength of 1.5 to 2 gigahertz, which means about 20 centimeters or so wavelength. So this guy wants to transmit to this guy. So a typical, today, what you might do is, you send in, you want to send your message. Your message might be a sequence of zeros and ones. You have a sequence of zeros. And then this is your message, let's say. Okay? You won't send this message directly. First, what you send is, you send a probe signal, some signal, you send it schematically. You send this out, you broadcast it. This guy receives it, okay? This guy receives it over here. What this guy will see is there will be some big blip and then some signal, okay? Stores this signal. This signal is being stored now. And as soon as the signal is stored, there is some, in the protocol, you're told that this is the probe signal. This information is sent out. Then the beginning of the transmission occurs with the signal coming through. When you receive this signal, you record it, and then you autocorrelate it. In other words, you take the Fourier transform of this signal when it comes in, you multiply it with the Fourier transform of this, it's the autocorrelation. And when you do that, that takes out, it's like taking out the effect of the medium, and you reconstruct the pulse, the signal. You reconstruct, when you autocorrelate the received signal with this, you reconstruct in some way the signal here. And you can do a study for this. How well are you doing? What's the bit rate that you can transmit? What's the bit error rate that can arise, and so on. This is nowhere near as good as doing the following, especially in a situation where energy considerations are important. And this is the matched field, let's say, standard way. The more dramatic way of doing this is this is the receiver and this is the transmitter, is for this guy to send in a probe signal first. So the receiver sends in a probe signal first, broadcasts it. Okay? Now this guy receives the signal at this end, stores it, a certain length of it, it's fairly long. Okay? And now time reverses this signal, encodes on this received signal, encodes the 0, 1, takes this signal, time reverses it, multiplies it by 0 and 1, and then sends it out, and he can send it out with an overlap, not just by waiting for this to complete before you send the next one. You can overlap them. And by doing that, because you're in time reversal, when the signal goes through the medium, it recompresses in time, but far more important, it compresses in space also. So it comes back and focuses on the receiver, and you receive the signal. Say if you were sending a signal that was like that, and then nothing, and then nothing. You send something like this. You would receive it at this end, time reversed, each pulse. But it would be very sharply, cleanly arranged, and it would be recompressed in time, because here it's stretched out in time, and compressed in space, which is remarkable, because it means that if you had somebody over here with a receiver, this guy would not receive anything. And of course, what is this distance? That's a mysterious number that you have to estimate. How close do you have to be before you can figure out what's going on? Well, it turns out theoretically, we know what it is. This is just of the order of it's lambda L over A sub B, where A sub B is the effective aperture. So all these concepts from time reversal come in right now. And there's a premium on finding what the effective aperture should be and how to implement this, how to work all these ideas into the communication protocol and find the properties of the protocol, how it behaves and what are the limitations in there. So this is what I had in this slide. Let me just see if there's anything in the slide that I have omitted. well, here is a little bit more mathematically. This is the signal that you send out. This is the probing pulse. This is what you receive at the transmitter. This is the time reversal protocol here. It's the Green's function convoluted with the f in the time domain. So this is the transmitter receives a piece of this. This is the part that you receive here, and you time reverse it. And now you simply send the signal out. This is the NJs are the information, zeros and ones, multiplied by the signal displaced by some delta. See, now they're going to overlap because this is going to be a long signal. Capital T is much longer than the delta, the original delta. So this signal, when it goes back through the medium, it will recompress and it will give you back perfectly clearly the original pulse time reversed, displaced by these units J delta, and then the signal will appear right there in the NJ. So, and I didn't even show the spatial resolution here. I didn't show you how you can determine the spatial compression, but you have some idea of how it might work. To conclude, I think that you have now some idea how time reversal and multipathing lends itself to some interesting, surprising, and important applications. And what is really fascinating for the mathematical or the mathematicians is that the mathematical infrastructure for understanding and using time reversal is largely underdeveloped. There are very few mathematicians who even understand what the problems are and can really, on their own, autonomously, without depending on somebody to tell you what you should be doing, to really decide what are the important issues and to go in there and to project your own ideas and compete. It involves the ergodic theory. It involves very deep mathematics, the ergodic theory of partial differential equations, deterministic and random, signal processing, communication theory, classical diffraction theory, computational wave propagation. You can't do anything without having a computational, the ability to simulate numerically what it is that you're doing so that you have some idea. I'm not an experimentalist. I cannot compete with people like Fink or others who do experiments. But we can do numerical experiments as well as anybody. And I think one of the reasons why the subject has been left behind is because people were not doing good numerical experiments before we got into this. So this is all I had to say. Thanks for your attention.
Questions? I have a quick question. What in this, for example, in finding targets or wireless communication, what is the role? What happens actually? I was thinking of the slowly varying component that bends a little bit the rays and so on. It just doesn't do anything? Does it help? It gets in the way?
It can be modeled. This is yes. The large-scale features of a medium, for example, I simplified for the. If you know something about the large-scale features of the medium, for example, in underwater acoustics, if you are in this off the coast of Italy, you know something about the large-scale topography, what it is, and you know a lot for features. You have from other information, topographic knowledge is there, and you can model it instead of back propagating in a homogeneous medium. That Green's function G0, which I modeled in a trivial way, can be modeled with some non-trivial model that has large-scale features, background variation, boundaries, what have you. Now, you may not know precisely where these things are. The uncertainty in your knowledge of the deterministic large-scale medium can be made part of the optimization problem in the matched field. So you know the medium up to, let's say, half a dozen parameters. You have an overabundance of data. You can throw those in along with the target locations and try to optimize over the parameters too. People do that. That's what, when people in underwater acoustics talk about matched field, they talk about that.